hello friends, welcome to lecture series on multivariable calculus. So, today we will discuss on extremum values, that is how to find maximum or minimum values of a function of several variables. So, let us first recall with a function of single variable. So, we know that if we have a function say y equals to fx, a single variable function y equal to fx, and domain is D suppose of this function, then a point x equal to c is said to be a point of absolute maxima of this function if f of x will be less than equals to f c for every x in D. Okay. If this hold, then we say that x equal to c is a point of absolute maxima. Similarly, if fx is greater than equals to fc for every x in D, then x equal to c we call as absolute minima. Now how can we check whether a point is a point of local maxima or local minima? So, we have second derivative test. So, x equal to a is a point of local maxima if f dash a equal to 0 and f double dash a is less than 0. We already know this result. Okay. If a is a point of local maxima, then the first derivative at a will be 0 and second derivative at a will be less than 0. We are assuming that the function is differentiable. Okay. So, x equal to a is a point of local minima if f dash a equal to 0 and f double dash a is greater than 0. A point where f double dash a equal to 0 and f triple dash a is not equal to 0 is called point of inflection. Okay. Say we have this example fx equal to x cube. So, when we take first derivative, it is 3x square and f dash equal to 0 implies x equal to 0. So, x equal to 0 is a critical point basically. Now, to check whether this point is a point of maxima, minima or point of inflection, we find second derivative. Now, second derivative is 6x and second derivative at x equal to 0 is again 0. Find third derivative. Third derivative is 6, which is not equal to 0 at x equal to 0. So, this means this point x equal to 0 is a point of inflection. Okay. Now, let us come to maxima minima of two variable functions. Say you have a function of two variable. Okay. So, a point a comma b will be a point of local maxima if f of xy will be less than equals to f of ab for some disk for all xy in some disk centered at a comma b. Okay. You take a point a comma b and there exists a disk centered at a comma b, and if for all xy belongs to that disk fxy is less than equals to fab, then we say that a comma b is a point of local maxima. Similarly, this ab is a point of local minima if fxy is greater than equals to fab for all xy in some open disk centered at a comma b. It must be open disk. Okay. So, if this inequality hold for every xy in some open disk centered at a comma b, then we say that a comma b is a point of local minima. Okay. So, we first have first derivative test. What is the first derivative test for local extremum values? So, if fxy has a local maximum or minimum value at an interior point a comma b of its domain, and if the first partial derivative exists there, then fx at ab is equals to fy at ab will be 0. Okay. Like in the single variable function, a function is differentiable and x equal to a is a point of local maxima or local minima, then f dash a will be 0. Okay. In a similar way, here for the two variable function, if the function if a point a comma b, which is an interior point, is a point of local maxima or local minima, and its first order partial derivative exists at this point, then fx at ab is equal to 0 and fy at ab is also equal to 0. Now, what is critical point? An interior point of the domain of the function fxy where both fx and fy are 0, or where one or both of fx or fy do not exist is called the critical point. So, basically critical point is a point where either fx equal to fy equal to 0 or fx or fy do not exist. Okay. Now, next is saddle point. A differentiable function fxy has a saddle point at a critical point a comma b if in every open disk centered at ab there are points xy where fxy is greater than fab and xy where fxy is less than ab. This point is called saddle point of the surface. So, in order to understand saddle point, let us discuss this example. So, fxy is suppose y square minus x square. So, first of all, saddle point is a critical point. So, first you find the critical point of this function. For critical point, we have three conditions. Okay. We have either fx equal to fy equal to 0, or fx or fy or both do not exist. So, the point where these two these two conditions hold, this or this condition hold, we say that point as critical point. Now, how to find the critical point of this function is clearly differentiable. So, you can find fx as minus 2x and fy as 2y, and fx equal to fy equal to 0 implies x equal to y equal to 0. So, the point is 0 0, 0 0 is the only critical point. Now, this point is a critical point. Okay. Now, if you take 0 comma 0 and take any neighborhood of 0 comma 0, I mean any open disk centered at 0 comma 0, any open disk. If you take any open disk centered at 0 comma 0, so there are some points which are on the x axis and there are always some points which are on the y axis. Okay. So, f at x comma 0 will be, for this function, will be minus x square, which is always less than f 0 0, which is 0. Okay. There is always some point on the x axis where the value of the function is less than 0, and if you take on the y axis, it is 0 comma y, which is y square here, and it is always greater than f 0 0, which is 0. If you take a point on the y axis, there are some points where the value of the function is greater than 0. Okay. No matter which open disk you are taking, whatever, for every open disk centered at this point, there are always some point on the x axis and there are always some point on the y axis, such that at some point this value is less than 0 and at some point this value is greater than 0. So, this means this point is a saddle point. Okay. Now, if we find fx and fy, okay, after finding the critical points, how can we check that a point is a point of local maxima, local maxima, local minima or saddle point. So, what is the second derivative test for two variable functions? So, let us suppose a comma b is a point of local maxima or local minima. So, if it is a point of local maxima and local minima and the first and second order partial derivative exist, then fx at a comma b will be equals to fy at a comma b will be equals to 0. This is by the first derivative test of local maxima or local minima. Okay. Now, take a point in the open disk of centered at a comma b, or take a point say a plus h and b plus k which is near to a comma b. Okay. Take a point a plus h and b plus k which is in the neighborhood of, which is in some open disk centered at a comma b. You can always find such point in the open disk centered at a comma b. Okay. Now, by the Taylor's theorem, for two variable functions, we know that f of a plus h b plus k will be equals to f a b plus f x at a b into h plus f y at a b into k plus 1 by 2 h square f x x plus k square f y y plus 2 h k f x y at a plus c h and b plus c k, where c lies between 0 and 1. So, this is by the Taylor's theorem of two variable functions. Okay. So, f of a plus h b plus k is equal to this result. Now, this is 0 because this point is a point of local maxima and local minima, and this is also 0. So, what we obtain from here? So, this implies f of a plus h b plus k minus f a b will be equals to 1 by 2 h square f x x plus k square f y y plus 2 h k f x y at a plus c h and b plus c k. Okay. Now, to see whether this point is a point of local maxima, local minima or saddle point, we have to see the sign of this. If a comma b is a point of local maxima, suppose, okay, if a b is a point of local maxima, that means the value of this, the value of function at this point will be less than this, because a comma b is a point of local maxima. Okay. So, the value of function at this point will be less than this. So, this value will be less than 0 and hence this must be less than 0. If a b is a point of local minima, then in the point, at the point near to a b, the value of the function will be more than value of the function at a b. So, the difference will be greater than 0. Okay. So, that means this must be greater than 0. Okay. And at saddle point, for some h k, this will be less than 0, and for some other values of h and k, this will be greater than 0 for saddle point. Okay. For saddle point, for some h and k, because h and k you can vary in that open disk, they may be positive and they may be negative. For some h and k, this value may be positive, and some other values of h and k, this values may be negative for saddle point. Okay. Hence, this values. Now, we have to only see the sign of this at this point. So, this will guarantee whether a point is a point of local maxima, local minima or saddle point. So, how can we say for this point, this function? Now, let us take this term as say q c. because it involves C. So, let us call it QC, which is h square f x x plus 2 h k f x y plus k square f y y at this point. Now, if QC is not equal to 0, then QC will have the same sign for sufficiently small values of h and k. If Q0, Q0, you can say Q0, take C as 0. If Q0 is not equal to 0, then this will have the same sign, or Q0, you can say Q0 will have the same sign for the sufficiently small values of h and k. You can always take the small values of h and k for which QC will have the same sign, no matter what C you are taking. Okay. You can take Q0. So, Q0 will be h square f x x at a comma b plus 2 h k f x y at a comma b plus k square f y y at a comma b, because when C is 0, the point will be nothing but a comma b. Now, we will simply see the sign of this function, I mean this value, this expression. If the sign of this expression is positive, no matter for some small values of h and k, okay. If the sign of this expression is positive for small values of h and k, then this means a comma b is a point of local minima. If this is negative, this means a comma b is a point of local maxima. So, now let us find out the sign of this. How can we do this? Let us see. So, let us suppose this is a h square plus 2 h k 2 b h k plus c k square. Suppose A is suppose this is A, capital A, suppose this is capital B, and suppose this is capital C. Okay. Now, make perfect square. You take A common, assuming A is not equal to 0. So, this will be h square plus 2 b by A h k plus c k square, assuming A is not equal to 0. So, this implies this is A h plus b by A into k whole square minus b square by A square into k square plus c k square, which is further equal to this is A into this, A into h plus b by A into k whole square minus b square by A into k square plus c k square. So, this will be equal to A h plus b by A into k whole square plus this is c A minus b square by A into k square. So, if you take A common from the entire expression, so this will be A square. Okay. Now, what is A? A is f x x at a comma b. What is b? B is this value and c is this value. Now, no matter whatever h and k you are taking in some open disk centered at a comma b, if you are calling a comma b is a point of local minima, say, if this is a point of local minima, then this implies f of a plus h b plus k minus f of a b will be greater than 0, because the point of local minima, that means in the in the point near to a comma b, the value of the function will be more than this value. So, difference will be positive. Difference will be positive means this must be positive, because this is equal to this value. Okay. So, this must be positive. Now this must be positive, for this must be positive no matter what h and k you are taking. So, a must be positive, this implies a is positive, and this must be positive, and this implies f x x at that point must be positive, and what is c? C is f y y minus f x x minus f x y square must be positive. So, this is the first condition for local minima. Okay. Now, if you check for local maxima, if you are calling a b as a point of local maxima, then f of a plus h b plus k minus f of a b must be less than 0, and this implies this quantity must be less than 0. For this quantity must be less than 0, what we are having? We are having a must be negative and this must be positive, because positive plus positive is always positive and multiply by negative value is always negative. If we take this value as negative value, then for some h and k this may be positive and for some h and k this may be negative. So, we can't guarantee that whatever h and k we are taking, this will always be negative. So, in order to guarantee this, we take a less than 0 and c a minus b square must be greater than 0. That is the first condition. Now, if this value is negative, whatever a may be positive or negative, it hardly matters. If this value is negative, then for some h and k this minus this may be negative, and for some h and k this and this minus this may be positive. So, in that case it will be a saddle point, because for some value for some h and k this is positive and for some h and k this is negative. So, a comma b will be a saddle point in that case, and if it is 0, so test will be inconclusive. We have to go for the higher order test to find out the nature of a and b. Okay. So, that is how we can find out whether a point x a b is a point of local maxima, local minima or saddle point. Okay. So, let us discuss first problem based on this. So, first problem is, it is x y minus x square minus y square minus 2x minus 4y plus 4 minus 2y plus 4. Now, you have to find local maxima, local minima and saddle point if exist for the following functions. So, first find critical points. So, how to find critical points? This function is very nice function, this is differentiable. So, you can find f x is y minus 2x minus 2 equal to 0, and find f y is x minus 2y minus 2 equal to 0. You have to find that point where f x equal to f y equal to 0, both are 0. So, that will be the simply point of intersection of these two lines, these two equations. Okay. So, what is the point of intersection of these two equations? This you can solve. So, point will be minus 2 minus 2, you will easily check, you can check also. So, point will be minus 2 minus 2, yeah, it is clear. Okay. Now, we have to check whether this point is the point of local maxima, local minima or saddle point. Okay. So, we first find f x x. What is f x x? F x x is simply you differentiate partially this again with respect to x, it is minus 2. So, f x x at point minus 2 is minus 2, which is negative. Now what is fyy? Fyy is again minus 2. So fyy at this point is minus 2. And what is fxy? Fxy is 1. So fxy at this point is also 1. Now what is fxx into fyy minus fxy square? This is equals to, this is minus 2 into minus 2 minus 1, that will be 4 minus 1, it is 3, it is positive. So fxx is negative and this value is positive, that means this point is the point of, from this result, this point will be a point of local maxima. Okay. So point minus 2 is a point of local maximum. Okay. Now let us try to solve the second problem. The second problem is fxy is equal to, this is 4xy minus x raised to power 4 minus y raised to power 4. So what is fx? For critical point fx equal to fy equal to 0. So this implies, first you find fx. Okay. What is fx? It is 4y minus 4x cube, which is equal to 0, implies y equal to x cube. Now fy is equals to 4x minus 4y cube equal to 0, implies x equal to y cube. Now we have to solve the values of x and y from these two equations. Okay. So you can substitute x equal to y in this equation. So what you will obtain, y is equals to y cube whole cube, that is y raised to power 9, and this implies y into y raised to power 8 minus 1 will be 0. This implies y raised to power 4 minus 1, y raised to 4 plus 1 equal to 0. Y into y square minus 1, y square plus 1, y raised to 4 plus 1 equal to 0, and this implies y equal to 0 or plus minus 1, 0 and plus minus 1, no real y here, no real y here. So when y is 0, x is 0. So points are 0 comma 0, when 1 it is 1, and when minus 1 it is minus 1. So these are the three critical points. Now we have to check which point is the point of local maxima, minima or saddle point. Okay. So we are having 3 points here, 0 0, 1 1 and minus 1 minus 1. So find fxx. What is fxx? It is minus 12x square, and fxx at first we check for 0 0. Okay. First we check for 0 0. At 0 0 it is 0. What is fxy? Fxy is 4. So fxy at 0 0 is also 4. And what is fyy? Fyy is minus 12y square, which is fyy at 0 comma 0 is 0. Okay. So you find fxx into fyy minus fxy square. If you find fxx for this point, if you find fxx into fyy minus fxy square, so this is 0 minus 16, which is less than 0. This implies this point is a saddle point. Now check for 1 comma 1. Okay. At 1 comma 1, this is minus 12, this remains same, and this value is again minus 12. So at 1 comma 1, fxx is negative, and what about this value? This value is minus 12 into minus 12 minus 16. Of course, it is positive. This is negative, this is positive, that means this point is the point of local maxima. Now again check for minus 1 minus 1. So what is fx at minus 1 minus 1? It is remain 12. For minus 1 minus 1 it is again 4. For minus 1 minus 1 it is minus 12. So the analysis remains the same, it is negative, and fxx into fyy minus fxy square is positive. So this point is again a point of local maxima. So in this way we can find out the nature of the points, nature of the critical points. So similarly we can also solve question number 3 and question number 4 to find out which point is the point of local maxima, local minima or saddle point. So thank you very much.